Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it, planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, NASA's chief scientist, and this is Gravity Assist. I'm here with Thomas Zurbuchen, the Associate Administrator for the Science Mission Directorate. Welcome, Thomas.
Glad to be here, Jim. So glad to be here.
Yeah, this is going to be great. We're going to talk about the solar wind. You know, the sun constantly exhales, and it does so in all directions, but man, it's just not steady. What's that kind of structure of the wind do we expect?
You know, the structure of the wind is really reflecting the structure of the magnetic field of the sun in a direct fashion. You know, if you look at the sun, of course it has a magnetic field, and at minimum it's like a bar magnet that is standing there. And so what's trying to happen is the magnetic field tries to pull in, right? Tries to keep the atmosphere there, and the gas wants to go out, the plasma wants to pull out. And so basically up there at the poles, right, there's far less pull in. It goes straight out, shoots right out along the magnetic field. So it's really fast wind at the top. Whereas around the equator of the sun, the magnetic field winds a lot more often, and it creates a mess, actually, a very structured, slower wind at the equatorial regions.
Yeah, in fact, that plasma, that solar wind just drags that field with it. And that's what really produces a lot of spectacular phenomena. You know, how does this wind change over the solar cycle? As you say, it's tied to the magnetic field, which goes through enormous changes.
Exactly right. So at solar minimum, it's more like a bar magnet. At solar maximum, it's a big mess, right? With active regions appearing at the surface. And frankly, we'd like to understand why and how exactly. We're not really good at predicting that. But we see these structures there, and they shape the entire solar wind in the heliosphere, making it much more structured at all latitudes, not just at low latitude like at minimum.
Well, you know, this is where Parker Solar Probe comes in. You know, we launched it several months ago. It's doing fantastic. What do you think Parker will find as it gets close to the sun?
So first of all, it's going exactly to where the answer is to that question. The question being, how is that wind actually get accelerated and heated? That heating happens really close to the sun, and Parker's going right there. So, you know, where we are right now is, you know, if I put like 10 or 100 scientists in a room and say, tell me what your ideas are about heating, you get 10 or 100 ideas, depending on how good they are, or even 200 sometimes, you know. And so basically what Parker will do is will provide data in a way that we've never had it, to actually exclude options. So we actually see whether there's kind of the last theory left standing, or like so what so often happens, Jim, as you know, is none of the theories really fit. So we're doing what is called learning.
Well, you know, I have my own theory as to what's happening. I don't think I've ever told you about that, but you know, because of the way the sun rotates on its surface, it moves faster at the equator than it does at the pole. But yet that magnetic field in the corona just seems to rotate like a rigid body. So to me, that means there must be all sorts of little micro reconnections going on, energizing that plasma and moving it forward.
And actually interesting thought, because we actually have data of such reconnections at these leading edges of these flows, right? Where kind of fast wind tries to overtake slow one. The magnetic field gets pushed into each other. And just like at the front of the magnetosphere, our magnetic protection layer at the sun, just like there, really highly structured interactions happen that cause the kind of connection that you just said, reconnections of the magnetic field that could lead to heating, like Parker or others actually predicted.
Well, you know, that's a fascinating story about Eugene Parker, and we were so lucky to have him down at the launch to watch this satellite. You know, how did that go? He was a real pioneer in the 50s talking about the solar wind that no one seemed to believe.
Oh, I think Eugene Parker is really a hero for all of us who have worked in this field. You know, he predicted, of course, that there is a solar wind, a supersonic wind that fills the heliosphere. And you know, at that time, that sounded crazy. Not only his enemies thought that, also many of his friends, right? And so he was really, I mean, he said he basically lost his job over that got hired just before he ran out of job. And then, of course, was proven right the first time we had these measurements up there, really consistent measurements of the solar wind. And what's exciting about Parker is that that's, that 58 paper we just talked about is the one paper that is very famous, but there's many more. I mean, you know yourself, right? You've, I'm sure, cited Parker on other things, whether it's reconnection, whether it's dynamos, whether it's, turbulence, whether it's concepts that relate to the topology and, how plasmas actually work. Parker is at the front and center. And, what better name to have on that rocket there as the Parker Solar Probe was lifting into the sky than him, because he's really been the foundation of that thinking.
I remember one of the major arguments that scientists were using against him, and that was, well, the sun is so massive, and it's going to require huge velocities of any material to be able to leave the sun. How could that possibly be? And indeed, there's got to be some acceleration mechanisms. And this brings me to my other question, and that is, we're finding out the sun is losing mass, and it's doing it in a really nifty way, the measurements that are being made that tells us that. Can you give us a little background on how that happens?
Well, so as the sun is blowing away its atmosphere, through that give and take process I talked about earlier, it's filling the space around it. And really is going into deep space, dragging, as you said, the magnetic field with it. And so we have, over time, with spacecraft, both near Earth, like ACE, the Advanced Composition Explorer, or WIND, by the way, in both cases with instruments that I worked on personally, but also over the poles, we've actually measured what that transport is of that plasma into deep space. So what happens, of course, it loses mass, a very minute amount of mass, I might add, compared to the sun itself. So that is not what the sun is going to die of, right? It's not the loss of mass. But it's also, of course, if you actually think about it, it's because it's spinning, right? It's like some ice dancer. It loses angular momentum. So it loses a little bit of speed in the rotation as well. Also a tiny, minute amount of that. But both of them very much measurable.
Yeah, so that tells us several things, Indeed, then, if you go back in time, when the sun had more mass, then it must have been also spinning faster. So these kind of things are really important to understand the evolution of our stars. Now, we make that measurement. What's really phenomenal to me is that measurement of the sun losing its mass. And we did that with the spacecraft you're well aware of, which is Messenger.
Oh, yeah. Yeah, Messenger, of course, is really pioneering spacecraft going in orbit around planet Mercury, the innermost planet, at, it's at its closest, about 30% the distance of the sun and the Earth, and its farthest about 42% of the distance. So it has kind of an elliptical orbit there. And we measured that very thing, measuring the angle of the flows down there at much closer than at 1 AU. And so, yes, we could measure precisely that flow and actually could calculate what the total mass flux is and the loss of momentum is from that. But that will be that instrument, that fast imaging plasma spectrometer, which is that instrument on that spacecraft Messenger, will always be the most important instrument for me, because it was the only instrument I've been involved in that I really built from scratch, from a drawing, a hand-drawn kind of idea, all the way to publishing data with it. And of course, a big orbit in between, Jim. It takes a long time to get to Mercury, and I just love that instrument.
Yeah, that's really been an exciting mission that we've talked a little bit about before, but it's so close to the sun, and it's had to have its heat shield and really mitigated all kinds of problems being that close. But it made spectacular measurements of not only the magnetosphere of Mercury, but what's going on in that magnetosphere. So Mercury is outgassing.
Oh, God. Yeah. I mean, so what we found, right, is that, of course, if you look at the environment of the planet, you see the solar wind. We just talked about that. It's actually, the solar wind is way more intense down there kind of barreling down on the magnetosphere, much more so than at Earth, for two reasons. A, there's more solar wind and stronger solar wind, but also the magnetic field is weaker at Mercury than the Earth. And so actually, depending on how much push there is from the sun during eruptions, mass ejections, it may actually push it all the way to the surface or near the surface. So because of that interaction with the surface, it actually, if you want, kicks off material. There's other reasons too, but that's one of them. That's sputtering, kind of the solar wind particles coming down and kicking off particles that were formerly part of the surface and putting them into the exosphere of the planet. It's called an exosphere, of course, because of the fact that the mass is small enough that it can't actually hold onto it and form a real magnetosphere like the Earth. So it's kind of, the particles are taking long hops and eventually escape far away. And so we measured that and found a lot of sodium and oxygen and, other components. But the sodium, interestingly enough, was the most relevant one, which many predictions, of course, did not get that right. But yeah, we're really excited to see that.
Even ground-based telescopes have seen this sodium tail flowing away from Mercury. It's just really spectacular.
Yeah, it's one of those big lucky coincidences. I always say, Jim, that, science discoveries and luck have a lot more to do with each other than science discoveries and planning. Of course, both is relevant, and we do both. But
Right.
in this case, the way this was discovered is this solar observatory looked up there at the sun with a filter with sodium on it. And if you know sodium, it actually has this very bright line that gets excited from the sun, and it stands out like a sore thumb, and kind of whether it's at the moon or whether it's at Mercury. And so there, where it's not supposed to be, the people wanted to look at the sun, kind of to the right of the sun, there was this really bright thing, and of course it was Mercury. And we saw sodium. Now, it's a lot easier to see sodium than, for example, oxygen or helium because of that specific atomic structure of sodium. And so when we went to Mercury and actually measured these particles, many people didn't believe that sodium actually was the most relevant contributor because of the fact that, it's so much easier to see from remote. And we know we've made that mistake before. Just because we see something because of a specific reason like this doesn't mean that it's the most important thing. Well, in this case, it was, certainly as far as the ionized exosphere is concerned.
Well, all that stuff flows in the solar wind, and it comes all the way out here, even to Earth sometimes. And so there's one mission you mentioned that is a real sentinel, and it's the ACE mission. So where is ACE, and what is it up to? It was launched in 1997. That's a long time ago.
Oh, yes. So ACE was one of the first missions I ever worked with, the Advanced Composition Explorer. It was designed to really measure the composition of samples of matter that are out there, starting with galactic cosmic rays, but then also solar energetic particles and solar wind. So it has the best measurement of the minute additions of heavy elements in the sun that we measure there with these very sophisticated composition instruments. By the way, there's one that's getting ready to be launched on Solar Orbiter that will go close to the sun that will eclipse that. But until now, it's the best measurements. And it's hanging out there, always looking at the sun at what is called the Lagrangian point. So it's kind of, if you look towards the sun, just imagine 1% the distance to the sun, like a million miles or so, is the Lagrangian point 1, as we call it. 2, by the way, is the reverse direction. That's where James Webb's going to be, but 1 is up there. So ACE is out there doing its turns like it has for a long time.
Yeah, the Lagrangian points seem to be such a mystery for so many people, but L1 in particular is really pretty easy to understand. L1 is that place where, as you go closer to the sun, the orbits get faster, and so the sun is pushing that spacecraft further, but it also is balanced by the Earth, which pushes it back because of the gravity of the Earth. And so that sort of allows that L1 to exist, that station keeping that can be done in that gravitational null between the Earth and the sun. It's a beautiful position. Now, it's far enough upstream that it measures solar wind that will eventually get to Earth. So how long of a warning do we get?
So depending on the speed of that solar wind, that's coming, of course, the distance is roughly the same and the speed is varying between, 350 to sometimes over 1,000 kilometers per second. It's in the 30 minutes to, less, or kind of around that kind of time frame. And so we see that, or even an hour, depending on at the lower end. We see those warning signs, and we see them coming, barreling towards the Earth, and of course, pushing in that magnetic shield, the magnetosphere, and causing all kinds of havoc, depending on what the magnetic field is that's carried in the solar wind, as you know.
Yeah, so that's a really neat little opportunity for us to get a heads up on what we call space weather, things that come to the Earth that's in the solar wind that can be really hard on the Earth. So in terms of space weather, how bad can it get?
Well, so space weather is with us all the time. So space weather affects us today. So if I was a radio communication expert that's using low frequency, radio, the state of the ionosphere, the charged upper part of our atmosphere, is given by space weather. There's many other elements that space weather affects right now, but it can get really, really bad. And so what's really bad about space weather is twofold. The first one is it can, under the worst circumstances, affect our space assets, whether those are for, TV or for GPS or whatever, the space mission, if you want, the NASA space mission can affect that too, just because it can get overwhelmed with energetic particles that are barreling down on it. What's actually more difficult for us is if it really pushes in on the Earth magnetic field. Like whenever you have these magnetic fields pushing down, it can cause currents that can overwhelm our electrical grids. And when that happens, it does so in a regional fashion. So imagine, of course, every once in a while, electric gets overwhelmed. If there's lightning, for example, somewhere, it knocks out a transformer. You've been in a place, right, Jim, where all of a sudden the light went out.
Right.
But imagine if that happened, a whole region, let's say the entire East Coast, all lights could go out. So if you think about that, frankly, we don't have enough transformers to go replace that in the worst case scenario, and it could take months or even years to replace that electrical grid. So that's the worst case scenario. Of course, it rarely ever happens, and certainly hasn't happened in the last 50, 100 years at that kind of level of intensity, but it can. There's absolutely no reason to assume that it cannot. And so for us, that's one of the things we're thinking about also.
Yeah, so monitoring the solar wind's just going to be an occupational hazard for us from here on, now that we know about it, and we know we really need to be on the lookout for it. Well, how far out does this solar wind go?
Well, so the solar wind gets out there, and just like radiation or anything, it thins out as it goes, right? So kind of if you want to get its pressure, its push against the environment, which of course is the galactic environment, it becomes weaker and weaker and weaker until all of a sudden the push back from the galaxy is just as high, right? And there's kind of a sphere out there, we call it, the heliosphere. The boundary of that is called heliopause. It just means it's over there, right? The heliopause. And that's out there at 120 times the Earth-Sun distance. So it's really approximately. So it's really quite far out there. And if you looked around there and collected particles around you, there's many more galactic neutral particles than there's solar wind. But it's still, the solar wind is still there. And just on the other side of that heliopause, there is basically the environment is entirely dominated, or very much dominated, by the galactic environment. So about 120 times the Sun-Earth distance, Jim.
Yeah, so that's the winds of other stars, so to speak, in addition to that neutral environment of particles that sort of drift around the galaxy. Yeah, now how we know that, of course, is from the Voyagers.
Oh, God, yeah. So, this mission, just like with you, right? The first book I ever got, Jim, had a picture of Voyager in it. And it's still in my office here at NASA, right? I got it from my godson under the Christmas tree. I remember when I was, just a few years old, and it talked about Voyager in the future. And what's amazing now, I'm turning 50 soon, right? The point is it's still doing amazing data. One of those Voyagers is out there at 143 times the distance of the sun and the earth, and it's out there in the galactic environment making the first measurements of humanity out there, and the other one is approaching at around 118 times the distance or so. He's approaching that boundary that we just talked about. So it's it's a great time right now. As I told you, it's kind of around 120 or so. It's close enough that it's getting exciting, Jim.
Right. So we might get another really spectacular opportunity for Voyager 2 to cross that heliopause, get some additional data. That's absolutely spectacular. Well, what future missions are being discussed to study the heliopause?
So it's a great time to ask that question, Jim, because we just started a new mission. It's called the IMAP mission. And what it actually does, it's near 1AU, since we just talked about the Lagrangian point. Actually, out there, we have a mission that's going to look at the particles that are flying in from that boundary out there, all the way from the outer edge of the heliosphere out there at the heliopause and its surfaces associated with it. And they're the neutral particles, of course. They're the only ones that can make it across the magnetic field. And it's basically a neutral particle telescope imaging that surface, and really with it imaging the processes that are going on at that boundary, the acceleration processes, the transport processes, and really the sources of these particles. And of course, with it, really studying such surfaces and analogs all over the galaxy and all over the universe. And so that's what IMAP will be about.
Yeah, man, what a fantastic time, learning how to do this kind of remote sensing that senses boundaries more than 100 astronomical units away. Just phenomenal. Well, I always ask my guests about their gravity assist. What event or activity that happened in the past that really accelerated them towards their goal of being the scientists that they are today. So, Thomas, what was your gravity assist?
It's actually super easy for me to remember because I remember it like it was today. And it's me walking into a coffee place in Switzerland, in Bern, where I was just about to finish my PhD. It was 1995. And I walked into there, and there was a guy sitting there. And he was talking to my professor, Professor Geis, who actually did the first solar wind experiment on the moon during the Apollo programs. But he was sitting there, and the guy, I know now, my friend, is Professor Len Fisk, who actually was in the job that I'm in the late 80s, early 90s. And he talked about science in a way I had not heard anybody talk about science. And I brought up the courage and did something I never did before or after, which is basically just walked up to the table and said, "Do you mind if I sit here and just listen?" And I took my coffee and I sat there. And what he did is he talked about science, and I just listened. I didn't say a word. All of a sudden he turned over to me and said, "Hey, what do you think about this?" So of course I had some ideas, and I told him, and I said, "Let's go to lunch." And after that lunch, he said, "You should come work with me," because he had left NASA and he was at the University of Michigan, and he built a group, and I was the first hire there. That was the beginning of a journey of mentorship, a gravity assist beyond comparison in my life, a person who became a friend. He was there, helped me with so many things, gave me opportunity, but also when my second child was born at 3 a.m. in the morning, he came there with his wife and watched my first child. So he became a friend as well. So my gravity assist was at that coffee shop, and it led to a life of mentorship, of friendship between us.
Well, thanks so much, Thomas. We really appreciated talking to you about the solar wind. Join us next time as I continue our discussions on the latest results from NASA research scientists. I'm Jim Green, and this is your Gravity Assist.